Today we're going to talk about inscribed angles. This can be defining a new thing that can be inside of a circle. We actually looked at this a couple of nights ago in an assignment question, but we didn't define what it was. In that question, we were given a circle, and we had a central angle, which we had defined, but then we had this other line coming in to make a triangle. And so in that lesson, in that set of homework problems, we were asked to find this central angle, and in that lesson we learned the central angle is the same size as the arc it cuts off. But then we were also asked to work our way back and find out what this angle was. And through the course of doing a few examples, hopefully we realized that there's a pattern to it, and that angle was half as big as the other angle. Okay? So this angle that has its vertex on the edge of a circle is called an inscribed angle. And that's what we're going to be talking about today. So the definition of an inscribed angle is an angle whose vertex is on the circle and whose sides are chords. So in that assignment, our diameter was one of the chords, but it doesn't have to be so. Just needs to be that the vertex is on the edge of the circle, and then that the two sides are chords that they cut across the circle. Then theorem 9.7 tells us about how big it is. It says the measure of an inscribed angle is equal to half the measure of the intercepted arc. So let's say, for example, that this arc is 120 degrees. That would mean that this angle is then 60 degrees. Okay. So a couple days ago we learned that a central angle, where its vertex is at the center, is the same size as the arc it cuts off. Or an inscribed angle, where its vertex is on the circle, is equal to half. We have a corollary here. There's a horrible typo. I'm a grammar person, and this drives me crazy. So if other two inscribed angles intercept the same arc, then the angles are congruent. So what that looks like is within a circle, if I have one inscribed angle here, okay, that particular inscribed angle is going to be half as big as the arc that's cut off. But I could draw any other inscribed angle as long as its ends are at the same place, and those two angles will be the same size because they cut off the same arc. Okay? Both of them are cutting off the exact same portion of the circle over here. So both of those angles would be exactly the same measure. The second corollary says an angle inscribed in a semicircle is going to be a right angle. So a semicircle, we learned, has its ends at the diameter. Okay, the diameter cuts it in half. So if we inscribe an angle in there, what we're going to do is put the ends of our angle on that diameter. And according to this corollary, that should be a right angle. Well, how big is a semicircle? 180. And if our theorem today said then inscribed as half of the arc, half of 180 would be 90. So any way that I draw an angle that has its ends on the diameter is going to end up being a right angle. No matter where the vertex hits on that semicircle, if the ends are on the diameter, these are all right angles. Okay. Any of those would be right angles. The next corollary says if a quadrilateral, what is a quadrilateral? Anything with four sides, and it doesn't matter what kind of quadrilateral it is, so it could be a special one, but it doesn't have to be, it just has to have four sides. So any sort of four-sided figure inside of a circle so that each of the vertices touches the edge, according to this corollary, says its opposite angles are going to be supplementary. So if I label those around, then for this particular picture, A plus C would have to equal 180, and B plus D would have to equal 180. The ones that are across from each other have to add up to 180. This is maybe a stretch to call a corollary. It's not maybe directly and abundantly obvious how this follows. But each of those angles, since they're on the edge, is an inscribed angle. So it does build from our inscribed angle theorem there. Okay, so the opposite angles are going to add up to 180. And the final one here, we have a theorem that says the angle that is formed by a chord and a tangent. So a chord cuts across the circle, a tangent brushes across the circle. So that angle that is formed by the chord and the tangent is equal to half the measure of the intercepted arc. So the intercepted arc is the arc that is cut off by the chord. It's the portion of the circle that the chord cuts off there. So if I would say for this problem, let's say that is 80, then that means this angle would be 40. So half is going to be important to us today. Two different kinds of angles. First, the inscribed angle, where its vertex is on the edge of the circle, is half the measure of its arc. And then this angle that's made by a chord and a tangent is half the measure of its arc. Questions? All right, we're going to look at some examples. All right. We need to find x and y in here. Can you tell me about x and y? They're both going to be 38. X and y will both be 38 because x and y both cut off exactly the same arc as the angle that's labeled 38. All three of them are cutting off that same portion of the circle. So if I trace out the 38, its edges hit right there. If I trace out the x, its edges hit right there. I missed on the tracing there, but pretend. And if I trace out the y, its edges also hit right there. All three of them cut off the same portion of the circle or the same arc. So we had a corollary that said all three of them would then be the same size, because they are all half as big as that arc. Okay, who can tell me about x or y here?
Supplementary.
They're going to be the same 25.
X is going to be 25. Why is x going to be 25? Because it's half as big as the arc that it cuts off. So x is across from that 50-degree arc, so x is going to be 25. An inscribed angle is half as big as the arc that it is across from. Now, how could I find out what y is? Something about the semicircle. So the point that is labeled there is important. There's a point put in the center there to let you know that this line that's drawn through is a diameter, that it goes through the center. And one of our corollaries said that if I have an angle in a semicircle, then what?
90 degrees.
It's a right angle. So this angle would have to be a 90-degree angle. And then we have a triangle. And what do we know about the angles of a triangle?
180.
They add up to 180. So we can subtract out from 180 to find that y must be 65.
You subtracted the arches.
We could also have subtracted the arc. So since we know it's a semicircle, it should have 180 degrees within that semicircle. So this other portion could be 130. And that arc across would then be half of the 130. So two different ways to approach the same problem.
you said.
You guys are silly.
Hey, I'm done.
No, we're not. I'm not. Stop belittling me. Doesn't even make sense. They're bullying me. You gotta help us out.
X is 7. X is 7.
Why?
Because it's across adjacent from 110.
Okay, so one of our corollaries said that angles that are opposite or across from each other in a quadrilateral or four-sided figure inside of a circle will need to be supplementary. Supplementary means to add to 180. So x is across from 110. Used to add up means that one must be 70. And what about y?
95.
They need to be across, that's not us. 95.
Wait, how did you figure that out?
One of our corollaries said that angles opposite of each other in a quadrilateral need to be supplementary or add up to 180. So the angles that are across from each other should add up to 180.
No, I did not.
Okay, x is the arc in this one, y is that angle. And we're given another angle in there, 60. So how can we find x or y?
X is 1.
X is 120. Okay, our first major theorem today said an inscribed angle is half as big as the arc. So 60 is half as big as 120. That arc should be twice as big as the angle. And then y, 60. Our second theorem today said an angle formed by a tangent and a chord is half as big as its arc and is cutting off that same arc x. So that angle y would be 60.
Because it's across from 120.
Because it cuts off the 120. Yep, it cuts off this arc here.
What's the X? What is
The x is the arc.
Okay.
So the arc is 120.
Why is that? Why?
The arc is 120 because it's should be twice as big as the inscribed angle. So the inscribed angle is 60, the arc needs to then be twice that big. Alright. How can we find one of the pieces of information we need here?
Why be half of 140?
Alright, so y is going to be half of something because it's one of those outside angles. What is it going to be half of?
The arc touches the arc.
It's going to be half of this arc
So it's
because that's the arc that's cutting off. How big is that arc?
80.
Why is that arc 80?
Because
Because it should be twice as big as the inscribed angle. So the inscribed angle is 40, that arc should be twice as big. So that arc is 80, which means y is 40.
Is it always the same as the inscribed angle?
Yes. Yep, because they're both half as big as the same arc. Now how can I find x?
The 2 arcs and at 360.
Okay, so one way to find x is to say that we're given a piece of information over here that's 150, and we just found this other arc is 80, so we could say how much of the circle have we used up by adding those together and saying that would then be 230. How much is left over then? 130. And how would that help us find x?
by 2.
Should be half as big as that, would be 65. Another way to work towards the same answer would be to say that across from the 150, that inscribed angle should be 75, and then within a triangle 180, and we could have subtracted out to find the 65. Two different ways to approach to find the same answer there. One final example. Okay, what do we know about x and y? They're going to be congruent. We have an isosceles triangle here, so they're going to be the same whatever they are. How can we find what they are?
Find the top angle.
Find the top angle. What's the top angle going to be? 40. 40. Inscribed angle, half of the arc. So if the arc is 80, that angle needs to be 40. Then within a triangle, subtract out, leaves 140 left over. So they both need to be 70. Right? Your homework problems are going to be very similar to these examples. They are going to ask you to find an x, y, and z within the pictures. Not just an x and y, but you'll have an x, y, and z to find. That comes from section 5 tonight.